Welcome to the Snoozy Scientist, where we gently explore the mysteries of our world, one sleepy yawn at a time. Wherever you are on this beautiful planet, this quiet corner was made just for you, a calm space where curiosity and science can meet, carrying you gently towards sleep. Tonight, we're going to drift back, far back, to the beginning of the sun's story, because hidden in its past is a mystery that has haunted scientists for decades. A story of family, of loss, and of shadows that may still reach across to touch us even now. For billions of years, the sun has been our constant companion. It rises, it warms, it guides. It is the silent metronome behind every heartbeat on Earth, the unwavering fire that has cradled oceans, forests, and entire civilizations. Steady, familiar, eternal. But what if the sun was never meant to shine alone? Because in the universe, loneliness is rare. Most stars, like the sun, are born in pairs, siblings, sometimes twins, born side by side in swirls of gas and fire. So, why does our star drift alone? For decades, some scientists wondered if the sun once had a twin, a star that slipped away into the galaxy long ago. A twin they gave a chilling name, Nemesis, a dark companion thought to stir the frozen edges of our solar system, slinging comets inward like cosmic arrows. The idea was simple, yet terrifying. If Nemesis exists, it could explain strange patterns in the fossil record, cycles of mass extinction, including the one that ended the age of the dinosaurs. If true, it would mean that Earth's story has been shaped not only by the sun's life giving warmth, but by the deadly shadow of a forgotten other half. And that thought leaves us with haunting questions. Why are most stars born in pairs, but ours shines alone? If the sun had a twin, where is it now? And if it is still out there, unseen, unmeasured, could it still shape Earth's destiny? Tonight, we'll search for the sun's forgotten other half, from terrifying hypotheses of a death bringing star to the quiet truth of the sun's lost siblings scattered across the galaxy. A story not of fiction, but of science, and perhaps of a truth more beautiful and more haunting than we ever imagined. But before we begin, I would love to know where in the world you're listening from and what the time is there. It is always fascinating to think of these stories being heard across so many different skies. If you enjoy these gentle journeys into Earth's distant past, please do consider leaving a like and subscribing to the channel. A warm thank you as well to those of you who are already subscribed. You're helping this little corner of the internet grow. So now, take a slow, deep breath, let your shoulders soften, and together, let's begin the story of the sun's forgotten other half. For as long as people have looked up at the stars, the night sky has felt like a canvas of solitary lights, each one shining alone against the dark. Yet when astronomers began to study them more closely, a very different truth emerged. Most stars are not loners at all. They are born together, paired in twos, sometimes even clustered in groups, linked by invisible threads of gravity. In fact, in our galaxy, binary systems are the rule rather than the exception. When astronomers began to count and classify, they discovered that nearly 2 out of every 3 stars, similar to our Sun, do not shine in isolation. Instead, they orbit with companions, tracing long elliptical paths around one another, like dancers locked in a cosmic embrace. Some orbit so closely that their surfaces nearly touch, pulling at each other's outer layers. Others circle at vast distances, thousands of times farther apart than Earth is from the Sun, yet still bound together by gravity's persistent pull. This discovery reshaped how scientists imagined star formation. When vast clouds of gas and dust collapse under their own gravity to form new stars, they rarely do so in perfect isolation. Turbulence, pressure, and rotation in the collapsing cloud often fragmented into multiple clumps. Each clump kindles its own star, and so what begins as one cloud often ends as a family. For stars like the Sun, it seemed that being born with a sibling was almost expected, which made our star an oddity. The Sun, steady and alone, appeared to stand outside the pattern. Astronomers looked at it with new suspicion. If so many other stars had partners, why not this one? Was the Sun truly unique, a rare solitary flame, or was there a missing chapter in its past? Some scientists suggested that perhaps the Sun's twin had once existed, but had been lost. Over billions of years, gravitational encounters can tear stars apart from their companions. Passing near another star, or drifting through the crowded tides of the Milky Way, a pair can be split, with one member flung outward while the other drifts on alone. Could this have been the fate of the Sun's twin, cast adrift into the galaxy, leaving our star seemingly solitary? The idea carried a haunting allure. If the Sun was born with a companion, then somewhere out there, far across the spiral arms of the Milky Way, a sibling star might still exist, glowing faintly in its own corner of space. Such a thought suggested that our solar system was not just an isolated family of planets circling a single star, but part of a greater story that had been fractured long ago. Yet the mystery deepened, because some astronomers proposed that perhaps the Sun's twin had not merely drifted away, but might still lurk nearby, unseen. They reasoned that if a faint star or a brown dwarf orbited at an immense distance, it could remain hidden from ordinary telescopes. Such an object, they thought, could exert subtle gravitational influence, stirring the outer reaches of the solar system in ways that might ripple inward. This suspicion was not born of imagination alone. When scientists compared the Sun's solitary nature to the statistics of other stars, the numbers were too striking to ignore. To find that nearly two-thirds of Sun-like stars have partners, while ours does not, raised a puzzle. In science, anomalies matter. They are often the cracks where deeper truths wait to be found. The Sun, with all its familiar light and heat, now looked like an outlier, and outliers beg for explanation. From this line of reasoning came questions that were at once simple and profound. If the Sun should have had a twin, then where is it? Did it escape across the galaxy billions of years ago, leaving us behind? Is it still out there, circling at a distance so great that we cannot yet detect it? Or did it ever exist at all? The possibility of a hidden companion star opened the door to ideas that reached far beyond astronomy alone. If such a twin had once shared the Sun's birth, it could have left imprints not only in the structure of the solar system, but also in the history of life on Earth. Scientists began to wonder if the Sun's missing partner might help explain mysteries that had long haunted the fossil record, patterns of destruction and renewal written into the very story of living things. And so the suspicion of a twin was not just about symmetry in the stars, but about survival and catastrophe on our planet. The Sun's loneliness was more than an oddity, it was a clue, and following that clue would lead scientists into one of the most dramatic hypotheses in modern astronomy, a theory that gave the Sun's lost companion a name. By the late years of the 20th century, whispers of the Sun's missing twin grew into something darker, something that blended science with a touch of myth. The idea was given a name that carried both weight and unease. It was called Nemesis, after the ancient spirit of divine retribution, the avenger who punished arrogance and restored balance through downfall. The very name seemed designed to stir a shiver of dread, as if the cosmos itself might harbor a patient executioner. The picture painted by astronomers was not of a bright, life-giving star like our own sun, but of something far fainter, a quiet ember adrift in the night. They imagined it as either a small red dwarf, with only a fraction of the sun's mass, or perhaps a brown dwarf, a failed star that never managed to ignite into full brilliance. It would be so dim and so remote that ordinary telescopes would never notice it, hiding in the distant reaches of the solar system where darkness reigns and cold holds dominion. Nemesis, if it existed, would circle the sun at a distance so vast it defied ordinary comprehension. Its orbit was imagined to take tens of millions of years to complete a single lap, a slow, patient journey around the outskirts of our cosmic home. Unlike planets and familiar moons, its path would stretch out into the icy deep, beyond the scattered Kuiper belt, and into the unseen halo of debris called the Oort Cloud. The Oort Cloud is one of the most mysterious structures of the solar system, a sphere of icy fragments and frozen remnants left over from the sun's birth. There may be trillions of objects suspended there, each one a silent relic of creation. Most drift in stillness, never straying far from their distant stations. But they are not anchored, they are fragile in their balance, easily disturbed by passing gravity. A single nudge could awaken them, setting them on a long fall inward, transforming them into comets with fiery tails sweeping toward the sun. The Nemesis hypothesis suggested that this faint star could be the unseen hand that stirred the Oort cloud. Each time its elongated orbit brought it near enough, it might send swarms of icy bodies tumbling toward the inner solar system. A few of those countless fragments, scientists feared, would eventually find their way to Earth, and in those moments, the sky itself would become the bringer of catastrophe, hurling fire and ice down on the fragile cradle of life. What unsettled people most was not the violence of Nemesis itself, but its patience. Unlike a supernova that blazes and dies in a single burst, Nemesis was imagined as something colder and more calculating. It would not roar suddenly into existence, but instead would quietly pass through its orbit, setting events into motion that would only unfold millions of years later. The terror lay in the idea of inevitability, of destruction written into the clockwork of the heavens. Scientists found the hypothesis strangely compelling, not only because it matched the pattern of other stars, but because it explained why the sun might not be truly alone. If most stars are born with companions, then perhaps our own star once had one too. And if it was faint enough, or distant enough, that might explain why it had evaded detection. The vastness of the solar system, stretching thousands of times farther than the path of Pluto, holds many secrets still hidden from human eyes. In that uncharted frontier, a dark twin did not seem impossible. Beyond the walls of academia, Nemesis also captured the public imagination. Newspapers and magazines ran headlines calling it the Death Star. Popular books described it as a lurking menace, waiting at the edge of vision. The idea of a second sun, dim and deadly, hiding in plain sight, was irresistible. It was the perfect mix of science, fear, and storytelling. Even though no one had yet seen this phantom star, the hunt was already alive, and telescopes across the world turned outward in search of it. The power of the Nemesis hypothesis lay as much in its atmosphere as in its equations. It suggested that life on Earth might not be subject only to chance or chaos, but instead to the cold rhythm of an invisible star. It cast the night sky not as a silent expanse, but as a stage where hidden players might shape the fate of planets. For a world still fascinated by the sudden disappearance of the dinosaurs, Nemesis felt less like a theory and more like a ghost story written in starlight. Thus, the quest began in earnest. Astronomers scanned the heavens with new purpose, developing instruments to peer deeper into the cold void, hoping to catch a glimpse of the companion that might be circling us still. In the eyes of many, the universe had just grown more dangerous, and the darkness beyond Pluto no longer seemed empty. It seemed haunted. When paleontologists first began piecing together the fossil record, they expected to find a story of steady progress, a gradual unfolding of complexity over millions of years. What they uncovered instead was far less orderly. Life surged in waves, blooming into extraordinary diversity, then suddenly collapsing into silence. Entire worlds seemed to vanish in geological moments, as if Earth itself had been struck by unseen blows that left scars across deep time. These collapses were not subtle, they were mass extinctions, moments when ecosystems broke apart and once dominant creatures disappeared forever. Coral reefs that had flourished for millions of years were gone in the span of a few millennia. Forests that blanketed continents withered almost overnight. Creatures that had ruled land and sea were reduced to bones buried in rock. The fossil record held the evidence like pages torn from a book, gaps where chapters of life had ended abruptly. As the collection of fossils grew and dating techniques sharpened, patterns began to emerge. Scientists noticed that these cataclysms did not always scatter themselves randomly across history. Instead, some thought they could detect a kind of rhythm, an eerie pulse that seemed to guide the rise and fall of life. Catastrophes appeared to return at intervals spanning tens of millions of years, almost as if an unseen metronome was ticking in the background of Earth's story. One of the most influential observations came in the early 1980s, when teams of paleontologists plotted the diversity of species over hundreds of millions of years. They were not searching for anything cosmic, they were simply charting life's growth and collapse. But what emerged from the data was unsettling. Mass extinctions seemed to fall in rough cycles of about 26 million years. It was as though time itself was divided into repeating chapters, each marked by destruction. The suggestion was haunting. If true, it meant that evolution was not just a tale of adaptation and survival, but also one of recurring loss. Life was not simply climbing a ladder of progress, but continually stumbling on steps that were missing. Each time the ladder was broken, new species filled the gaps, but the scars of collapse remained etched in stone. The most striking scar of all was left by the dinosaurs. For more than 150 million years, they reigned over Earth, spreading into every shape and size imaginable. They grew into towering giants that thundered across floodplains, sleek predators with teeth like knives, and even delicate bird-like forms that flitted among trees. Their reign seemed eternal, yet about 66 million years ago it ended in what, on geological scales, was the blink of an eye. Entire lineages disappeared, leaving only birds as their living heirs. The evidence pointed to an asteroid impact in what is now Mexico. The collision unleashed firestorms, earthquakes, and global darkness. Plants withered, food chains collapsed, and within a short span of time, the age of dinosaurs was over. But while this event stood out in its violence, scientists began to ask whether it was part of a broader pattern. Were other extinctions also tied to cosmic events? And why did they seem to cluster in such regular intervals rather than arriving randomly? The fossil record whispered of other great vanishings. Trilobites that had once filled ancient seas were swept away long before dinosaurs appeared. Mammal-like reptiles, once dominant on land, were toppled in sudden die-offs. Even the smallest life forms told their stories. Layers of limestone rich with microscopic plankton suddenly gave way to barren rock, their disappearance marking moments of invisible crisis. Each absence was a reminder of life's fragility. This growing sense of rhythm unsettled the scientific community. If extinctions repeated with a strange regularity, what was keeping the time? Was the pattern driven by Earth itself, with continents shifting, volcanoes erupting, and climates turning hostile in great convulsions? Or was something larger at play, something beyond the boundaries of our planet, exerting its influence from the wider cosmos? The idea of a hidden order behind extinctions was both fascinating and terrifying. It suggested that life's rise and fall was not only the result of adaptation or chance, but also of forces far greater than Earth itself. The possibility that an unseen clock might be ticking overhead gave these patterns an almost mythic weight. As researchers debated, the fossil record continued to grow, sharpening the picture. Each discovery added new detail to the puzzle, but the sense of mystery remained. The rocks told a story of resilience and vulnerability intertwined, of life pushing forward only to be cut short again and again. Somewhere in those patterns lay a truth about the forces that shape existence, and so the mystery deepened, guiding scientists to turn their eyes outward as well as inward. If the rhythm of destruction could not be explained by Earth alone, perhaps the answer was waiting in the sky, hidden among the stars. Once the idea of Nemesis took hold, astronomers turned their attention to the night sky with renewed urgency. The notion that a hidden companion star could be orbiting at the fringes of the solar system was not only compelling, it was testable. If such a star existed, however faint, it should leave behind a trace of its presence, some faint signature written in the starlight. The earliest searches were conducted with traditional telescopes, the same kinds of instruments that had revealed planets, moons, and galaxies. Astronomers swept carefully across the sky, looking for tiny shifts or subtle patterns that might betray a dim star moving slowly against the backdrop of more distant suns. Yet the farther they looked, the more they realized how vast the search would need to be. Beyond Pluto, the solar system spreads into unimaginable distances. A star drifting out there, cold and dim, could hide almost anywhere. The challenge was one of light. Our sun burns brilliantly, filling our skies with warmth, but red dwarfs and brown dwarfs glow with only a faint ember's heat. To an ordinary telescope, they would appear almost invisible. Searching for Nemesis was like trying to find a dying coal in the middle of an endless desert night. This was where a new kind of technology offered hope. By the late 20th century, astronomy had moved beyond visible light and into the realm of infrared. Infrared telescopes could detect heat instead of light, allowing astronomers to glimpse objects too cool and faint to shine in the usual way. Stars that had failed to ignite fully, the brown dwarfs, might still radiate enough warmth to reveal themselves to infrared eyes. The hunt for Nemesis began to shift into this invisible spectrum, and with it came the possibility of success. Ground-based infrared observatories started to comb patches of sky, but Earth's atmosphere is restless and full of heat of its own, blurring the view. To truly see the cold edges of space, astronomers needed to rise above the atmosphere entirely. This is where space-based telescopes entered the story, carrying instruments into orbit to capture the faintest warmth from objects that ordinary starlight could never reveal. The most ambitious of these efforts came in the early 21st century, when NASA launched the Wide Field Infrared Survey Explorer, known simply as WISE. This mission was designed to scan the entire sky, not in visible light but in infrared, collecting a map of the universe as it had never been seen before. With its sensitive detectors cooled to extremely low temperatures, WISE could pick up the glow of objects that were otherwise invisible, from nearby brown dwarfs to distant galaxies hidden behind clouds of dust. If Nemesis was real, WISE should have been able to find it. The telescope scanned billions of stars, cataloging countless sources of faint warmth across the heavens. For years, astronomers sifted through its data, searching for the telltale motion of a nearby companion drifting through the solar neighborhood. They expected, perhaps, to find a dim ember orbiting at great distance, confirming decades of suspicion. But as the data came in, Nemesis was nowhere to be seen. WISE found no evidence of any star-sized companion orbiting the Sun. The space beyond Pluto was revealed in unprecedented clarity, and the supposed executioner of mass extinctions simply was not there. What WISE did uncover, however, was no less astonishing. The survey revealed an entire population of brown dwarfs scattered through the galaxy, many of them closer than previously imagined. It discovered star forming regions hidden behind veils of dust and cataloged tens of thousands of asteroids and comets within our own solar system. Instead of confirming Nemesis, it reshaped our view of the cosmos itself, opening a window into a universe that had been cloaked in darkness. The search for a hidden twin star had ended without the answer many expected, but it had not been wasted. In looking for Nemesis, astronomers discovered a far richer tapestry of stars and worlds than they had ever anticipated. The night sky, once thought to be well charted, revealed itself as deeper and more mysterious than before. And yet, the absence of Nemesis did not erase the questions. The cycles of extinction still needed explanation, and the sun's loneliness remained a puzzle. The fossil record still bore scars of sudden endings, and the sun still shone alone in a galaxy where most stars are born with companions. The search had ruled out one possibility, but it had also widened the horizon of mystery, pointing scientists toward new paths of discovery. From here, attention began to shift. If Nemesis was not lurking in the shadows, then perhaps the truth lay elsewhere. Perhaps the sun's story was not about one sinister twin, but about an entire lost family scattered across the Milky Way, waiting to be found again. For a time, the idea of Nemesis held on tightly. It seemed to explain too much, to tie together too many mysteries, to be easily dismissed. But science is not about what feels compelling. It is about what can be tested, checked, and measured against the weight of evidence. And when the evidence was gathered more carefully, the story of Nemesis began to unravel. The first cracks appeared in the very foundation of the hypothesis, the fossil record itself. In the early days of analysis, the pattern of extinction cycles looked neat, almost mechanical. Every 26 million years, a pulse of destruction, as though the heavens were keeping a grim schedule. But as paleontologists gathered more fossils, as dating methods improved, and as gaps in the record were filled, the rhythm began to falter. The extinctions did not fall with the steady beat of a metronome. Instead, they arrived irregularly, some closer together, others stretched out over longer spans of time. There were long quiet intervals without catastrophe, and clusters of smaller extinctions that did not fit the model at all. The clock in the sky that Nemesis was supposed to wind began to look more like an illusion, the product of incomplete data rather than a hidden truth. At the same time, astronomy itself was reaching new levels of precision. If a companion star had been out there, circling in the shadows, it should have been visible with the right tools. That was where the Wide Field Infrared Survey Explorer, NASA's WISE mission, became so important. WISE was launched to scan the entire sky in infrared light, a kind of heat vision for the cosmos. Unlike visible light, which can be blocked by dust or simply fade to invisibility for cold objects, infrared reveals the warmth that even the faintest stars still emit. If Nemesis had been a red dwarf glowing dimly, or a brown dwarf carrying the leftover heat of a failed star, WISE should have spotted it. Over the course of its survey, WISE scanned hundreds of millions of stars and objects, creating the most detailed infrared map of the sky ever assembled. If there had been a star-sized object orbiting within even a couple of light years of the sun, it would have glowed in those data. Astronomers combed through the results, searching for anything that might betray the presence of Nemesis. They found new brown dwarfs elsewhere, and they revealed asteroids and comets in far greater numbers than expected. But when it came to a hidden twin star orbiting the sun, there was only silence. This silence was loud in its own way. With the sensitivity of WISE, the absence of evidence became powerful evidence of absence. The parameter space where Nemesis could still hide shrank smaller and smaller until eventually there was nowhere left for it to remain. The outer solar system was not haunted by a lurking twin after all. The dark companion was gone, not because it had left, but because it had never been there in the first place. For some, this conclusion carried disappointment. There is a human tendency to prefer neat answers, stories that tie mysteries together in a single satisfying thread. Nemesis had offered that thread, binding the fossil record to the stars, connecting Earth's fragility to the deep rhythms of space. But as the evidence mounted, the scientific community reached a consensus. Nemesis, elegant though it was an idea, was not real. Extinction cycles were not regular, and no hidden star had been found. Yet this was not a failure. In science, disproving an idea can be just as powerful as confirming one. The search for Nemesis had driven technology forward. It had inspired missions, sharpened our view of the sky, and deepened our fossil analyses. It had introduced the public to the fragility of life and the vast scale of cosmic time. And along the way, it revealed something even more beautiful than a single dark twin, a galaxy full of hidden stars, of faint companions, of entire families of suns scattered across space. The death of Nemesis as an idea did not close the door on the sun's missing companions. Instead, it widened the search in a new direction. If not one twin star, then perhaps many siblings, born together in the same stellar nursery, now scattered across the galaxy like distant relatives waiting to be rediscovered. The question shifted, but the curiosity did not fade. The search for Nemesis eventually faded, but what it left behind was not emptiness. Instead, it opened the way to a different and far more profound truth. Even if the sun did not have a single deadly twin, it was almost certainly not born alone. Stars do not emerge in solitude. They are born in company, together in swarming clouds of gas and dust that collapse into brilliant clusters. When astronomers look deep into our galaxy, they can see these stellar nurseries glowing faintly in the darkness. Vast molecular clouds stretch for light years, cold and dense, until their own gravity pulls them inward. Inside these clouds, knots of matter collapse into blazing newborn stars, often dozens or even hundreds at a time. From afar, such regions appear like tiny nests of light, each point a young sun, burning for the very first time. Our own sun was once part of such a place. About 4.5 billion years ago, it emerged from a giant cloud rich with hydrogen and helium, a cloud already seeded with heavier elements by earlier generations of dying stars. The birth of the sun was not an isolated event. Around it, other stars ignited too, sharing the same cosmic cradle. In its first moments of light, our sun was surrounded by a family of siblings, stars that shared its chemistry and its birthplace. These siblings would have filled the early skies with brilliance. If Earth had existed then, it might have looked upward and seen not only our sun, but dozens of other bright stars shining closer than any neighbor we see today. Some of those siblings may have been small and faint, glowing red with the light of dwarfs that will outlive even our sun. Others may have been far larger, burning with blue-white intensity, destined to live fast and die young in spectacular explosions. Together, they formed a crowded family, huddled close in the same stellar nursery. Over time, that family began to drift apart. Gravity, though it binds stars together in galaxies, does not hold small clusters forever. The pull of the wider Milky Way stretches and scatters, tugging at each sibling until they slowly separate. In a few 100 million years, the sun's birth cluster unraveled. The siblings carried away into new orbits around the galactic center. Some may still travel near enough to one another to be cousins in motion. Others have long since wandered to distant parts of the galaxy, anonymous among the billions of stars that crowd the night. For astronomers, The knowledge that the sun had siblings changes everything. It means our star's story is not singular, but part of a family history. By searching for those siblings, scientists can learn about the environment in which the sun was born. They can uncover the chemistry of the cloud that shaped Earth, the radiation fields that bathed the newborn solar system, and the stellar events that enriched it with the heavy elements needed for oceans and life. The sun's siblings are like scattered pages of a diary. Each one holds a fragment of the same origin story, written in their elemental makeup and in the path of their journey through the galaxy. Finding them is like reassembling that diary, piecing together the family history that Earth itself has long since forgotten. What makes this story even more remarkable is the sheer number of siblings the sun once had. Astronomers estimate that its stellar nursery may have birthed not just a handful, but dozens or even hundreds of stars. Some would have been nearly identical to the sun, others wildly different, but all were family, born from the same cloud and shaped by the same forces. And somewhere, out in the galaxy tonight, many of them are still burning. They are distant now, scattered across thousands of light years, but they shine on, carrying within them the same ancestral fingerprint as our own sun. To find them is to look into a mirror of the past, to glimpse the company that once shared the cradle of our star. The search for Nemesis may have ended, but the quest for the sun's true family had only just begun. When stars are born together, they rarely remain together for long. Stellar nurseries may begin as crowded gatherings, but they are fragile against the pull of the galaxy. Over time, these clusters unravel, their bonds loosened by the restless dance of gravity. What begins as a family soon becomes a scattering, siblings drifting away into the wide dark until they are separated by unimaginable distances. Astronomers can see this process in action when they look at young clusters today. Some are only a few million years old, still wrapped in the gas and dust of the clouds that created them. In these newborn gatherings, stars press close together, their combined glow lighting the darkness like lanterns in a fog. But already, the forces that will scatter them are at work. The mass of the galaxy pulls in every direction, the great spiral arms tugging, twisting, and stretching the cluster until its members wander apart. The Milky Way is not a still place. It is alive with motion, every star circling the galactic center in a path that takes hundreds of millions of years. In these journeys, clusters pass near other stars, giant clouds of gas, or the dense arms of the spiral itself. Each encounter adds a nudge, a gravitational tug that reshapes the family's cohesion. Over time, these nudges accumulate, loosening the bonds until siblings slip away, one by one. What was once a tight cluster becomes a dispersing stream, and eventually nothing remains but solitary stars, indistinguishable from the countless others around them. This is what happened to the sun's birth family. Roughly 4.5 billion years ago, when the sun first ignited, it did so alongside many siblings. They may have orbited one another loosely for a time, caught in the gravitational web of their shared nursery. But as the cluster aged, the galaxy's tides began to scatter them. Slowly, steadily, each star was carried onto its own path until the family broke apart completely. The scale of this scattering is difficult to imagine. A sibling star that once burned brightly near the sun might now be thousands of light years away, hidden in a completely different region of the Milky Way. Others may still pass relatively near, moving like distant cousins in parallel orbits, but with no obvious sign of their shared origin. To an observer on Earth, they would appear as ordinary points of light in the night sky, anonymous among billions. What makes this dispersal especially poignant is that the sun's siblings are still out there. They have not vanished. They still burn, carrying within their atoms the same chemical fingerprints as our sun, but they no longer look like family. They shine now as strangers, spread across the galaxy, each living out its own destiny. Some may already have ended their lives in violent supernovae, scattering heavy elements back into space to seed future generations of stars. Others may still be shining quietly, their light perhaps reaching Earth even now, though we do not yet recognize them as kin. Astronomers sometimes describe this dispersal as a kind of cosmic diaspora, a scattering of stars that once belonged to a single cradle. Unlike human families, these stars cannot write or remember their shared past. Yet the evidence remains written in their chemistry and in the subtle traces of their motion through the galaxy. The challenge is to find those traces, to gather the siblings back together, not in space, but in knowledge. The sight of today's star clusters offers a glimpse of what the sun's earliest sky might have looked like. If Earth had existed at that time, its nights would not have been empty and dark, but filled with an abundance of brilliant lights, some far brighter than any star we see now. To think of those skies glowing with family is to understand what has been lost in the passage of time. Now, the sun travels alone. It circles the galactic center with only its planets and comets for company, a solitary wanderer in a crowded galaxy. But the story of its siblings is not gone. It lingers in the Milky Way, waiting to be uncovered, waiting for astronomers to follow the faint trails back to the family that once was. For a long time, the stars were little more than distant pinpricks, each one a quiet light with its own private story. As telescopes improved, those stories began to open. Astronomers learned to read starlight the way a botanist reads tree rings, slowly and patiently until patterns emerge. Among those patterns was a possibility that felt both intimate and vast at the same time. Somewhere in the crowd of the Milky Way, there could be stars that are not just neighbors, but relatives born from the same cloud as our sun. By the early years of the 21st century, the tools to look for such family ties were finally in hand. When a star's light is spread into a spectrum, it carries a barcode of sorts. Every element in a star swallows very specific shades of light, leaving narrow dark lines in the spectrum. Iron leaves its marks, carbon leaves its marks, magnesium, silicon, nickel, and many others leave theirs as well. The exact recipe of those lines is a chemical fingerprint, and stars formed from the same cloud tend to have nearly matching fingerprints. It is not proof in the way a birth certificate might be, yet it is compelling and it can be checked. With that promise, teams began scanning nearby stars, measuring their spectra with great care, and then comparing those measurements to the sun's own signature. The Milky Way holds hundreds of billions of stars, most of them strangers. Only a tiny fraction could be siblings. Finding them would be like recognizing a familiar face in a city that stretches from horizon to horizon. Still, the search was worth the effort, because a true match would do more than satisfy curiosity. It would let us reconstruct the neighborhood where the sun and earth were born. In the year 2014, that patient work paid off. A group of astronomers announced that they had identified a nearby star whose chemical fingerprint was strikingly similar to the sun's. The star bears a catalog name that is not poetic, yet it is precise. Astronomers call it HD 162826. It lies roughly 110 light years away in the direction of Hercules. With the naked eye, it is unremarkable, one faint light among many. In a spectrograph, however, it becomes something else entirely. Its elemental abundances line up with the sun's in a way that is difficult to dismiss as coincidence. HD 162826 is not a perfect look-alike. It is a bit larger than the sun and somewhat hotter. To an observer who only judged by color or brightness, it would not be an obvious match. The kinship appears in the details that only careful instruments reveal. Ratios of iron to silicon, traces of rare elements, the delicate balance of volatiles and refractories that reflect the chemistry of the original cloud. Those balances are as telling as accent and cadence in a human voice. Listen closely, and you can hear the same origin echoing through the light. Chemistry alone would have been suggestive. Paired with motion, it became persuasive. The European Space Agency's Gaia Observatory was built to measure stellar positions and motions with exquisite precision. With its help, astronomers can rewind a star's path through the Milky Way, tracing where it was long ago. Stars born together begin their lives moving together, and although time and galactic tides eventually scatter them, some memory of that common path remains. For HD 162826, the reconstructed motion and the chemical fingerprint pointed in the same direction. It likely formed in the same stellar nursery as our Sun more than 4.5 billion years ago. That realization changed the search from a dream into a map. If one sibling could be found, then others could as well. The method was now clear. First, narrow the field using motion, looking for stars whose orbits through the galaxy could plausibly have once overlapped with the Sun's. Then, test the chemistry with high-resolution spectra, comparing line by line to the Sun's pattern. The matches will be rare, because most stars formed elsewhere, but the rare ones matter most. Each one is a surviving page from the Sun's family album. The discovery also stirred questions that reach beyond starlight. If a sibling star carries the same chemical recipe, what kinds of planets might have gathered around it when its disk cooled and clumped? Would rocky worlds there share familiar ratios of elements, the same raw materials that on Earth built continents and oceans and in time life? HD 162826 has not yet yielded an Earth twin, but the possibility is no longer fanciful. It is a question to be answered with careful surveys and years of quiet patience. There is a gentle comfort in the idea that our Sun's first companions are still out there. Most will be far away by now, scattered by the wide tides of the galaxy. Some may already have burned through their fuel and ended in storms of light. Others may be shining steadily, their photons already halfway here. We do not know their names yet, but we know how to look. The chemistry is a lantern, the motions are a path. Together they turn a crowded sky into a place where family can be recognized. Finding HD 162826 did not close a chapter, it opened one. It showed that the Sun's early world can be reconstructed, not from memory, but from measurement, and that the clues are written into the stars themselves. With that first clear sibling identified, the next step is to follow the trail with better maps, finer spectra, and the quiet confidence that more relatives are waiting to be seen, each one carrying another small piece of the story we are telling now, step by step, as we learn how to find them. Finding one solar sibling was a triumph, but it also raised an even greater challenge. If the Sun truly had dozens or even hundreds of siblings, then how could we recognize them among the hundreds of billions of stars spread across the Milky Way? The answer lies in two tools that turn astronomy into something like detective work: chemistry and motion. Every star carries within its light a unique fingerprint. When the glow of a star is split into a spectrum, dark lines appear where different elements absorb their favorite colors. These lines form a pattern, and that pattern is different for each star, depending on the cloud of gas and dust it came from. Stars that were born together in the same cradle of gas will share almost identical patterns. It is as if they carry the same genetic code, a cosmic version of family resemblance, written not in DNA, but in starlight. This method of identifying family ties is called chemical fingerprinting. It requires careful observation because the lines are delicate and subtle. Yet with modern spectrographs, astronomers can measure abundances of elements like iron, silicon, magnesium, and carbon with exquisite precision. When two stars show the same unusual balance of these ingredients, it is a powerful clue that they were born in the same nursery. Chemistry, however, is only part of the story. To trace family, astronomers also need to know how stars move. Every star drifts around the Milky Way in a long orbit that takes hundreds of millions of years to complete. Over time, siblings are pulled apart by the tides of the galaxy, scattered like seeds in the wind. Yet, even after billions of years, their motions still carry echoes of that shared beginning. If you can rewind the orbits, you can sometimes find the moment when stars once clustered close together. This is where the Gaia mission has transformed the search. Launched by the European Space Agency, Gaia is a space telescope that maps the positions and motions of more than a billion stars with extraordinary accuracy. It can measure the tiny shifts in a star's position as seen from Earth, changes so small that they are like watching a hair's breadth move on the surface of the moon. From these measurements, astronomers can calculate how each star is moving through the galaxy, where it has been, and where it is going. By combining Gaia's motion maps with chemical fingerprints, scientists can work backward in time. They can ask whether a particular star might once have shared space with the Sun, and whether its chemical pattern matches the recipe of our own star. It is a process of elimination and confirmation, sifting through millions of possibilities to find the few that fit both tests. In many ways, it feels like reconstructing a crime scene. The fossil record on Earth provides the timeline of what happened here, while Gaia's data provides the positions of potential suspects across the galaxy. The chemistry then steps in as the final piece of evidence, confirming or rejecting the relationship. One by one, the stars are questioned, and one by one, most are dismissed. But sometimes, the data line up just right, and a sibling is revealed. This work is slow, but it is filled with wonder. Imagine holding a spectrum of starlight and realizing that the tiny dips in color are telling you about events that happened 4.5 billion years ago. Imagine tracing the motion of a star across space and realizing that it once shone beside the sun, when the solar system was only dust and sparks. These are not just measurements, they are fragments of a forgotten childhood, recovered with tools of light and mathematics. The detective story is still unfolding. For every sibling found, many more remain hidden. Some have wandered so far that their kinship will never be provable. Others may be close, shining down on Earth every night, their chemistry waiting to be read. The search continues, driven by the quiet certainty that our sun was never alone, and that its family can still be found if we know how to look. The story of the sun's siblings is not only about distant stars scattered across the galaxy, it is also a story about why Earth itself became a place of oceans, air, and living things. The conditions of the sun's birthplace did more than light up the night sky. They helped set the stage for Earth to emerge as a habitable world, while other planets nearby did not share the same fortune. When the sun was born, it was not alone. It formed in a crowded stellar nursery, a dense pocket of gas and dust, where dozens, perhaps hundreds of stars were ignited almost at once. That environment shaped everything that followed. The chemistry of the cloud, the density of the cluster, and the level of nearby activity all contributed to the recipe that would one day determine whether Earth could hold oceans, build a stable atmosphere, and nurture a crust strong enough to last for billions of years. Inside that nursery, the mixture of gases and dust was crucial. Lighter gases, such as hydrogen and helium, were plentiful, but the nursery also contained heavier materials stirred in from past generations of stars. Those heavier ingredients gave the solar system the ability to form solid rocky planets instead of only gas giants. Yet the role of siblings here is more than chemical. The very arrangement of the nursery influenced how the early solar system survived its first moments. The cluster was filled with powerful neighbors. Radiation from nearby stars could have stripped Earth's building blocks away before they settled. Shock waves from massive explosions could have shredded the solar system's disk of gas and dust before planets took shape. But the sun seems to have been born in a rare balance. It was close enough to other stars to inherit the right chemistry, but not so close that those stars destroyed the fragile beginnings of the planets. This delicate balance allowed Earth to grow steadily, gathering material, cooling its surface, and eventually holding liquid water. The contrast becomes clear when we look at the other worlds that formed alongside Earth. Venus is nearly the same size as our planet, yet its path diverged sharply. Its atmosphere thickened into a choking shroud that trapped heat until its surface became a furnace. Mars, by comparison, was too small to hold on to its air and water. Though it may once have had rivers and lakes, its atmosphere slipped away, leaving a cold desert of dust and rock. Both worlds remind us that habitability is not guaranteed. Earth's oceans and breathable air were the outcome of conditions set in motion at the very beginning in the nursery shared with its siblings. By studying those siblings, astronomers can trace back the influences that made Earth habitable. Each star born in the same cluster carries a chemical and environmental signature of that shared beginning. Some of those siblings may now host planets of their own. If any of them carry seas or atmospheres, it would suggest that the nursery favored habitability for more than one world. If others turned barren, it would reveal just how narrow the path was for Earth to become what it is. This pursuit is not abstract, it connects directly to the ground beneath our feet and the air we breathe. Earth's ability to hold water on its surface, to stabilize its climate, and to support life depended on an extraordinary sequence of circumstances. The sun's family environment helped set those conditions. Without that starting point, Earth might have ended up like Venus, wrapped in suffocating heat, or like Mars, stripped bare under a thin sky. The siblings scattered across the Milky Way are, in a sense, mirrors of what could have been. Some may reveal familiar beginnings, others may reflect paths where habitability never took hold. By finding them, scientists hope to understand not only the family story of the sun, but also why Earth, among so many possibilities, became a blue planet filled with oceans, forests, and life. The study of these siblings deepens our sense of fragility. Earth's habitability was not inevitable, it was shaped by chemistry, timing, and the quiet influence of a stellar family that has long since dispersed. The answers written in those stars may explain why our world has rivers that flow and skies that shelter life, while so many others remain silent. Long before the sun came to life, the galaxy was already filled with echoes of older stars that had burned bright and died in spectacular fashion. Some of those stars were so massive that their lives lasted only a few million years, brief by cosmic standards. They ended not with silence, but with explosions so immense that they could outshine an entire galaxy for a fleeting moment. These explosions, called supernovae, were more than endings. They were the universe's way of scattering seeds. Inside every star, matter is slowly reshaped. The crushing heat and pressure fuse light atoms into heavier ones, a process that lights the star's fire. A modest star like the Sun can forge elements such as carbon and oxygen during its lifetime, but the truly massive stars go further, building layer upon layer of heavier elements inside them, like the concentric rings of a tree trunk. Yet even their power has a limit. When the core fills with iron, fusion can no longer continue. Iron resists the process, demanding more energy than it gives back. At that moment, the star's delicate balance collapses. The collapse is violent and swift. The core implodes in an instant, then rebounds outward with a shockwave of unimaginable force. This is the moment of the supernova. In the chaos of that explosion, matter is thrown into conditions so extreme that elements heavier than iron are created. Gold, uranium, and countless other rare atoms are forged in less than a heartbeat. The star tears itself apart, its remains flung across interstellar space. What seems like destruction is also creation. The atoms released by supernova are the raw materials of everything familiar. Without those explosions, the universe would be a simple place, filled mostly with hydrogen and helium. There would be no richness of matter, no iron for strong bones, no carbon for the molecules of life, no oxygen to bind into water or flow into lungs. Every one of these elements is a gift of a dying star. This heritage can be traced in the smallest details of our existence. The iron that courses through blood, carrying oxygen to every cell, was born in the collapse of ancient giants. The calcium that hardens bones was pressed into being in the fiery heart of a massive star. The carbon that forms the backbone of DNA, the molecule that encodes life, came from the same process. Even the gold that humans value and wear as jewelry is a reminder of stellar death, atoms scattered into space billions of years before the Earth was formed. The story is everywhere, hiding in plain sight. In every raindrop is oxygen that once blazed in a star's core. In every breath of air is nitrogen born from the fusion of long vanished suns. In every grain of soil is silicon released in the scattering winds of explosions older than memory. The world we know is built from fragments of long dead stars. Astronomers sometimes describe this cycle as the galaxy's great act of recycling. Nothing is wasted. Each generation of stars takes in what the last has left behind. When they shine, they forge. When they collapse, they return their work to the universe, to be gathered again by new clouds, new suns, and new planets. The sun's birth was not the beginning of this chain. It was one link in a story stretching back billions of years, one chapter written by the lives and deaths of stars. The sun's lost siblings share this inheritance. Each one carries the same elemental recipe, the same fingerprint of explosions that enriched their shared birthplace. By studying their light, astronomers can measure exactly which atoms those long ago supernovae contributed. Each sibling is a kind of witness, holding a piece of the evidence of how the solar system was made possible in the first place. The deepest truth revealed by these explosions is both humbling and intimate. Life itself is a continuation of stellar death. Every heartbeat is powered by atoms that were shaped in ancient fire. Every thought in the human mind, carried by electrical signals through neurons, depends on sodium, potassium, and phosphorus that were once scattered as ashes across the galaxy. Supernovae may be violent, but they are also the reason anything more complex than hydrogen exists. They are both destroyers and creators, sculpting the very fabric of matter. Without them, there would be no worlds with mountains, no seas, no living things, no stories told beneath starlight. The universe would be empty of all detail. And so, in every raindrop that falls, in every breath drawn, in every trace of iron coursing through blood, the history of those explosions continues. They are not gone. Their echoes are carried in every atom of life, every stone of earth, and every light in the night sky. The sun's birth was possible only because of them, and through us, those ancient deaths are still alive. When we think about life on Earth, it is tempting to see it as something sealed away, an isolated story told only here on this planet. Yet the deeper scientists look, the more they begin to wonder if life might be part of something larger, something that stretches beyond Earth itself. One of the most intriguing ideas is called panspermia, a word that means seeds everywhere. It suggests that the first microbes may not have begun here at all, or at the very least, that fragments of Earth's life may have once traveled outward to other worlds. At first, the idea seems almost impossible. Space is harsh, with freezing cold, intense radiation, and the vacuum of emptiness. Yet studies of microbes on Earth have revealed something extraordinary. Some of the tiniest and most ancient forms of life, including hardy bacteria and single celled organisms, can survive under conditions that would kill almost everything else. They can endure intense heat, extreme cold, and long periods of dormancy. Some have even been found alive after being trapped in salt crystals or ice for millions of years. These microscopic survivors make it easier to imagine life clinging to a rock hurled through space. Asteroids and comets strike planets with enormous force, sending up plumes of shattered rock that can escape into orbit. Scientists believe that chunks of Earth have been blasted into space many times by such collisions, and that Mars too has sent fragments of its surface flying outward. Pieces of Mars have been found here on Earth, lying quietly in deserts and frozen lands until their Martian origin was uncovered. If rocks can move between worlds within a single solar system, the possibility grows that under the right circumstances, they could cross even greater distances. This is where the Sun's siblings enter the story. In the crowded nursery where the Sun was born, stars would have drifted close to one another, tugging at the disks of dust and planetesimals surrounding them. Gravitational nudges may have thrown comets and asteroids on long, wandering journeys. Some of those icy messengers might have carried not just frozen gases, but also microbial passengers. In such moments of exchange, material from one young world could have landed upon another, carrying within it the potential for life to take root. Imagine the scene: two young stars passing near each other, their newborn planets still cooling, their disks thick with dust and ice. A comet stirred loose from one system could sweep across the gap and fall toward another star's family of worlds. If it carried hardy microbes sheltered deep inside rock or ice, it might deliver more than water or minerals. It might deliver a spark of biology. The question is breathtaking in its scope. Did Earth's life truly begin here, or is it part of a greater network of living seeds shared among stars? If microbes can survive the journey, then the possibility arises that life in our galaxy may not be confined to a single place. Instead, it might be woven across multiple systems, cousins scattered far and wide, all linked by the exchanges of those early stellar nurseries. There is also the reverse possibility. Perhaps Earth did not give away life, but instead received it. The first cells may have arrived in a fragment of rock that fell into Earth's oceans billions of years ago, carried from a sibling star's world. In that case, our very beginnings would be tied not just to Earth's chemistry, but to the fortunes of an ancient cosmic family. Even today, scientists search for evidence that could confirm or deny such a story. Experiments on the International Space Station have shown that some microbes can survive years exposed to the edge of space. Studies of meteorites reveal complex organic molecules, the raw ingredients of life, formed in deep space without any planet at all. Each new discovery pushes the boundary of what seems possible. The idea of panspermia does not lessen the wonder of Earth's life. Instead, it adds another layer of awe. It means that when we look at ourselves, we may not only be children of Earth, but also heirs of the stars, shaped by exchanges that took place when the galaxy itself was young. And if that is true, then somewhere across the Milky Way, there may be other planets carrying the same inheritance, their oceans stirred by the same chemistry, their creatures descended from the same tiny travelers that once clung to rock and ice. When we look into the night sky with the naked eye, we see stars scattered across a black canvas, each point of light appearing solitary and distant. Yet many of those stars were not born in isolation. They began their journey as part of a family, crowded together in glowing nurseries. Some of those families are still visible today, preserved long enough for us to witness them with our own eyes. They give us a rare glimpse of what the sun's childhood may once have looked like. Among the most famous of these stellar families is the Pleiades, often called the Seven Sisters. In truth, the cluster contains hundreds of stars, but only a handful can be seen clearly without the aid of a telescope. To the human eye, they appear as a tiny cluster of bright blue sparks, gathered close as if huddled together against the darkness. The Pleiades lie about 400 light years away, which is close in cosmic terms, making them shine with remarkable clarity in our skies. Ancient cultures across the world noticed them, weaving them into myths and stories. Yet behind those stories lies a scientific truth. These stars are young, only about 100 million years old, still burning with the fierce hot light of youth. In many ways, the Pleiades are a time machine. They show us what the sun's birthplace might have looked like. Imagine standing on Earth nearly 5 billion years ago, when the sun was newly born. The sky would not have been a quiet spread of distant stars, but a crowded tapestry of siblings shining together. Some would have glowed blue and massive, destined to burn out quickly in supernovae. Others would have been smaller and cooler, more like the sun, built for endurance. The sight of so many stars gathered close would have been breathtaking, and it is something we can still glimpse today when we turn our gaze to the Pleiades. Another living example is the Hyades, a cluster much older than the Pleiades and spread wider across the sky. The Hyades form a V-shaped pattern in the constellation Taurus, marking out the head of the celestial bull. Unlike the compact Pleiades, the Hyades have had time to drift apart, their stars now scattered into a looser family. They are about 600 million years old, and that difference in age shows in their appearance. The brilliant blue stars of their youth have already burned out, leaving behind redder, cooler stars that shine with a steadier light. The Hyades remind us that star clusters do not last forever. Gravity binds them only for a time before the tides of the galaxy begin to pull them apart. This is the fate that befell the sun's own family. Billions of years ago, its siblings scattered across the Milky Way, carried away by the slow churn of galactic forces. The Hyades, half dissolved yet still visible, are a living echo of that process. When we look at them, we see not only a cluster of stars, but also a mirror of what may have happened to the sun's long-lost companions. There is something deeply human about these clusters. For as long as people have looked up, the Pleiades and the Hyades have served as markers of time and season. Farmers watched their rising and setting to know when to plant or harvest. Sailors used them to navigate across oceans. Poets and storytellers found in them tales of family, love, and pursuit. Yet behind the myths, the clusters carry a scientific story that is even more profound. They are windows into the earliest stages of star birth, a chance to observe how families of stars are formed, evolve, and eventually dissolve into the wider galaxy. Astronomers study these clusters not only for their beauty, but for what they reveal about stellar life cycles. The Pleiades, with their youthful blue glow, allow scientists to study the early years of stars, from their spinning disks of dust to the planets that may still be forming around them. The Hyades, with their greater age, reveal how clusters mature, how their most massive stars die young, and how the survivors drift apart. Together, they form a living sequence, showing us different chapters of the same story. When we connect these clusters to the sun, they take on an even more personal meaning. They show us that our star's lonely existence today is not how it began. The sun was once part of a crowded sky, surrounded by dozens, perhaps hundreds of siblings. Seeing the Pleiades and Hyades is like glimpsing the faded family album of the cosmos, a record of what once was, still visible in the heavens above us. From here, the story of stellar families begins to bend toward loss. For if clusters like the Pleiades and Hyades are still together, even partially, then what happened to the sun's companions? The answer lies in the slow scattering that time brings, the unraveling of once close families into distant strangers shining far apart across the galaxy. The stars of a cluster are born close, gathered tightly in a nursery of gas and dust, bound by gravity into a shimmering family. But that closeness never lasts. Time stretches long in the life of a star, and the forces at work in a galaxy are vast. Little by little, the bonds that once held a cluster together begin to weaken, until what began as a crowded family becomes a scattering of wanderers across the Milky Way. For the sun and its siblings, this unraveling began almost as soon as they were born. A star cluster is like a delicate weaving of light, but the threads are constantly tugged by forces outside themselves. The disk of the galaxy, rotating steadily, creates tides of gravity that sweep through clusters like waves moving through a net. Each pass pulls at the stars, loosening them, shifting them slightly from their companions. With every million years, the pull grows stronger, and the once tight knit family begins to spread apart. Encounters with massive molecular clouds add to this scattering. These clouds are the raw material for new stars, immense billows of hydrogen and dust that stretch for light years across space. When a cluster drifts near one of these giants, its gravity tugs at the stars, warping their paths. Some are pulled outward, set on new trajectories that carry them away. Others are nudged just enough to drift further from the heart of the family. A single encounter with such a cloud can reshape an entire cluster, and across billions of years, the sun's family would have passed by. Many. Close approaches between stars themselves also play a role. In the crowded early days of a cluster, stars sometimes pass near one another, each tugging gravitationally on the other. It is a quiet interaction, nothing like a collision, yet it can redirect paths, sending one star closer to the center while pushing another out toward the edge. Over time, enough of these small nudges add up, slowly breaking the group apart. The Milky Way itself contributes as well. The galaxy is not empty space, but filled with invisible structure. The spiral arms are regions of higher density, where stars and clouds cluster more thickly. As families like the sun's drift through these regions, they are stirred and stretched, scattered by the gravitational tides of the larger galactic structure. Slowly, almost imperceptibly, the stars are set loose, drifting further and further from the cradle that once held them. The irony of this scattering is that it may have been a blessing. If the sun had remained in the close company of its siblings, Earth's story might have been very different. A crowded cluster can be a dangerous place for planets. Supernovae erupt nearby, flooding the region with radiation. Close passes from other stars can tug at planetary systems, destabilizing orbits, even stripping worlds from their suns. In such a place, Earth might never have had the calm, stable environment it needed to nurture life. By drifting away, the sun found solitude, and in that solitude, Earth found safety. The separation that ended its cosmic family may have been the very thing that allowed oceans to form, forests to spread, and civilizations to rise. Each sibling went its own way, scattering across the Milky Way, but in that scattering was the gift of stability. The Earth could spin quietly around its star, undisturbed by the chaos of a crowded cluster. Now those siblings are far away, scattered across the galaxy as points of light that no longer reveal their kinship to the eye. Yet their shared origin remains, written in the chemistry of their atmospheres and the motion of their paths. Scientists searching for them trace these hidden clues, reconstructing the family that time and gravity pulled apart. From here, the story of the sun's lost brothers and sisters becomes not only one of scattering, but of memory, for even if the family is dispersed, it is not gone, and to find those siblings, scattered and distant though they may be, is to look deeper into the origins of Earth itself. When scientists look for the sun's lost siblings, they are not simply tracing an old family tree for the sake of curiosity. Each sibling carries a memory, a hidden record of the time and place where they were born together. In a way, they are like time machines. By studying them, astronomers can reach back billions of years into an age before Earth had oceans, before continents had risen, before even the first spark of life. The key is written in the stars themselves. Every star holds in its light a chemical fingerprint, a unique mixture of elements forged in the cloud that gave it birth. These fingerprints do not fade with time. They are like ancient signatures waiting to be read. If two stars share the same balance of elements, it is a strong clue that they once formed side by side in the same stellar nursery. By comparing those chemical signatures, scientists can reconstruct the conditions of the sun's earliest environment, as though unlocking a vault that has been closed for over 4 billion years. The Gaia spacecraft, launched by the European Space Agency, has become one of the most powerful tools in this search. Gaia traces the precise motions of stars, measuring tiny shifts in their positions as they drift across the galaxy. With these measurements, astronomers can roll the clock backward, calculating where each star was in the distant past. When they find a star whose path intersects with the sun's birthplace and whose chemical fingerprint matches, they know they have found a true sibling. This is more than a coincidence of motion, it is a shared history. Through this method, scientists are beginning to rebuild the scene of the sun's lost childhood. They picture a crowded cluster filled with dozens or perhaps even hundreds of stars, all glowing newborn and hot. The cluster would have been alive with energy, a place where radiation streamed across space, where winds from young stars blew gas into sculpted shapes, and where massive stars lived fast and died in supernovae, enriching the cloud with heavy elements. In this environment, the cloud that would form the sun and earth was stirred, compressed, and enriched, setting the stage for a solar system that could host life. By studying the siblings, astronomers can estimate how much radiation bathed the young sun, how much pressure was exerted by nearby stars, and how many heavy elements filled the surrounding gas. These details shape the story of Earth itself, the balance of carbon, oxygen, and iron in our world, the conditions that allowed oceans to condense and life to begin, all trace back to this crowded nursery. Without the siblings, the picture would remain blurry, a half remembered dream. With them, it comes into focus. It is as though each sibling star carries a fragment of a puzzle. One star may tell us about the temperature of the birth cloud, another about the distribution of dust, another about the timing of nearby explosions. Together, they form a record of the sun's earliest environment, an environment long since erased in our corner of space. Where Earth orbits now, the traces are gone, swept away by time, but in the scattered siblings, the memories remain. There is also a more personal layer to this work. To know the sun's siblings is to know something about the long story of survival that made Earth possible. If the cluster had remained together, life here might never have emerged. If the sun had been born in a more violent neighborhood, Earth might not exist at all. By tracing the siblings, scientists are learning not only about the past, but also about the delicate balance of chance and circumstance that led to a world of seas and forests, of human voices and quiet dreams. Each discovery of a new sibling deepens that understanding, adding one more thread to the tapestry of the sun's origins. Together, they remind us that our star is not an isolated wanderer, but part of a story written across the galaxy, a story that begins in a crowded cradle of light and still echoes in the stars around us. And as the search continues, the siblings guide us further back, showing us not only who we are, but where we came from, and how the very first chapters of Earth's story were written in starlight. When astronomers look out across the night sky, they often find stars that appear strikingly similar to our sun. These stars shine with the same yellow-white glow. They are nearly the same size, and they burn at almost the same temperature. At first glance, they could be mistaken for the sun's long-lost twin. Such stars are sometimes called solar twins. They mimic the sun so closely that if placed side by side, even careful instruments would struggle to tell them apart in brightness and color. But similarity is not the same as family. A solar twin is a star that resembles our sun, yet it may have been born in a completely different cloud, light years away, under conditions that shaped it into a near match. Just as strangers can sometimes look uncannily alike without being related, solar twins are coincidences of nature rather than true kin. They are fascinating to study since they show us what the sun might look like if placed in another context, but they do not carry the shared history of birth alongside our star. Solar siblings, on the other hand, are a very different story. These are stars that actually emerged from the same giant cloud of gas and dust that gave birth to the sun over 4.5 billion years ago. They may not always look like perfect twins. Some may be larger, others smaller, some slightly hotter, others cooler. Yet what connects them is their shared origin. They were born in the same stellar nursery, cradled in the same swirl of enriched material, and scattered only later by the restless pull of the galaxy. The way astronomers tell the difference is through chemical fingerprinting. A true sibling shares the same elemental recipe as the sun. When a star is born, the mixture of hydrogen, helium, carbon, oxygen, and heavier elements it inherits from its birth cloud is locked into its light. This recipe is so distinctive that it can act like DNA, marking stars from the same birthplace with a common signature. A solar twin may look like the sun, but if its chemistry is different, the illusion of kinship fades. A sibling might look different in brightness or color, yet the chemistry betrays its true family bond. This distinction matters deeply for astronomy because it changes the questions we can ask. A solar twin can show us how common sun-like stars are in the galaxy, giving us a mirror for comparison. They are useful for estimating how ordinary or rare our sun might be among billions of others. But a solar sibling can reveal something much more intimate. By studying siblings, scientists gain a glimpse into the exact environment that shaped Earth's birth. Each sibling star carries evidence of the radiation, the dust, and the heavy elements that once surrounded the young sun, and therefore carries clues about why Earth became habitable. The search for solar siblings has also opened new questions about life elsewhere. If siblings carry planets of their own, those planets would have been formed in nearly the same environment as Earth. The odds that some might share Earth-like chemistry, with oceans or atmospheres capable of sustaining life, become tantalizingly higher. These are not just worlds around look-alike stars, but around family members, stars that once shared the same cradle as our sun. The poetry of this distinction is striking. A twin is a mirror, a reminder of how the sun might appear elsewhere. A sibling is a storyteller, holding a piece of our origin and whispering of the time when the sun was young. For astronomers, separating these categories is not just about labels, but about uncovering the truth of how stars, planets, and life itself come to be. As the search continues, instruments like Gaia and powerful spectroscopes will help us tell twins from siblings with ever more precision. Among the vast sea of stars, only a precious few will carry the chemistry and motions that mark them as true brothers and sisters of the sun, and through them we continue to trace the sun's childhood, hidden in the distant glow of stars scattered across the Milky Way. When scientists learned how to look beyond our solar system, they began to discover planets circling distant stars. These worlds, called exoplanets, now number in the thousands, each one a tiny revelation that planets are not rare, but a natural outcome of stars being born. Some are enormous giants, larger than Jupiter, with storms so vast that Earth could disappear inside them. Others are scorched deserts, clinging close to their parent stars. And then, among these alien landscapes, a few worlds emerge that seem hauntingly familiar, rocky and small, with the right size to remind us of home. The search for Earth like planets has always been more than a scientific quest. It is also a search for kinship, for another blue world under another sun. And when astronomers speak of solar siblings, stars that were born from the same cradle as our own, the pull of imagination deepens. If Earth's oceans, mountains, and forests were shaped in part by the chemistry of that ancient stellar nursery, then might not one of the sun's lost siblings carry a planet of its own, formed from the same enriched cloud of gas and dust? The odds are not impossible to imagine. In stellar nurseries, countless disks of material swirl around newborn stars, and many of these disks condense into planets. If the sun gave rise to a world like Earth, then perhaps another star born beside it could have done the same. Such a planet would not only share Earth's cosmic origin, but might also share the rare conditions that allow oceans and atmospheres to exist. It could carry within it the same balance of carbon, oxygen, and iron that make life possible here. In a quiet, stirring way, that possibility hints at cousins to life itself, distant relatives scattered across the galaxy. The search is guided by light. When a planet passes in front of its star, even briefly, it dims the star's glow. Sensitive telescopes can catch this flicker, measuring the size and orbit of the hidden world. At other times, astronomers watch the subtle wobble of a star tugged by the gravity of an unseen planet. These tiny signals have revealed more than 4,000 worlds already, and the number continues to grow with each passing year. Among them are planets orbiting stars that resemble the Sun, and a few may orbit stars that are not only similar, but family. What makes the idea so moving is the personal scale of it. If life exists on such a world, it would have risen under a star that once blazed beside our own sun, long before the galaxy pulled them apart. Imagine standing on the surface of such a planet, looking upward, and knowing that your sky was once lit by the same fires that gave birth to Earth. In that sense, the search for exoplanets among the Sun's siblings is not just a search for distant rocks, it is a search for other homes, other oceans, and perhaps even other stories of life that echo our own. Powerful observatories now make this dream more tangible. The Kepler Space Telescope opened the first great chapter, finding entire families of planets circling stars far away. Its successor, the Transiting Exoplanet Survey satellite, widened the map, scanning almost the whole sky for signs of new worlds. And now, the James Webb Space Telescope offers the ability not just to find these planets, but to peer into their atmospheres, searching for the fingerprints of water vapor, oxygen, and other gases that might hint at the presence of life. What lies ahead is even more extraordinary. Future missions are being designed to block the overwhelming glare of a star so that the faint glow of its planets can be seen directly. These instruments may one day take the first true picture of a pale blue dot circling another star. If such a world were found around one of the sun's siblings, it would be like gazing into a cosmic family portrait, seeing Earth's reflection preserved in another corner of the galaxy. The possibility of such discoveries lingers at the edge of our imagination. It suggests that Earth may not be the only place where oceans glisten in the sunlight, where winds sweep across continents, or where life stirs in the shadows of distant trees. Somewhere out there, under the light of a familiar star, another world may already exist, waiting to be found. And so the search continues, each telescope scan adding another piece to the puzzle. Among billions of stars in the Milky Way, a handful may hold the closest answers to the question that has followed us since the dawn of time. Are we alone, or are we simply one branch of a much greater family? To search for the sun's long-lost siblings, astronomers need more than curiosity and imagination. They need instruments capable of sifting through the glittering sea of the Milky Way, separating chance lookalikes from true kin. It is a task that demands precision on a scale almost beyond comprehension, because in a galaxy of hundreds of billions of stars, the family of our sun is scattered like grains of sand across a beach. The most powerful tool in this search is a spacecraft called Gaia, launched by the European Space Agency. Gaia's mission is to chart the positions and movements of stars with exquisite detail. As it circles Earth, Gaia measures the locations of nearly 2 billion stars, recording their brightness, their distances, and the tiny shifts in their positions as the spacecraft moves. These shifts, no larger than the width of a human hair, seen from thousands of kilometers away, allow scientists to calculate how each star drifts across the galaxy. By tracing these motions backward in time, astronomers can look for stars that once moved in harmony with the sunday. If a group of stars shares not only a chemical fingerprint but also a common journey through space, it is a strong clue that they were born together. Gaia turns the Milky Way into a kind of time-lapse photograph, showing not only where stars are now, but where they came from. This ability to reconstruct the past makes Gaia the cornerstone of the search for the sun's siblings. But motion alone is not enough. To truly identify family, astronomers also need to study the light of stars, splitting it into its component colors through a technique called spectroscopy. When starlight is spread into a rainbow, dark lines appear where elements absorb specific wavelengths. These lines are like barcodes, marking the presence of hydrogen, helium, carbon, oxygen, iron, and countless other elements. No two stars have exactly the same pattern, but stars born from the same cloud share nearly identical ones. This is why astronomers often compare spectroscopy to DNA testing. It allows them to confirm not just resemblance, but shared ancestry. With these two methods, motion from Gaia and chemistry from spectroscopy, the picture of the sun's scattered family begins to emerge. But the search does not end with identifying siblings. Once a sibling star is found, the question deepens. Does it host planets of its own, perhaps even ones like Earth? This is where the next generation of telescopes enters the story. The James Webb Space Telescope, orbiting far from Earth's atmosphere, is able to study the faint light of distant worlds with extraordinary sensitivity. When a planet passes in front of its star, Webb can capture the thin veil of starlight that filters through the planet's atmosphere. Within that light are hints of gases like water vapor, methane, and carbon dioxide, all of which are pieces in the puzzle of habitability. If one of the sun's siblings were to reveal such a world, it would be like finding a second chapter to Earth's story written under the glow of a familiar star. Future observatories are being designed to push this search even further. Concepts like the Nancy Grace Roman Space Telescope and proposed missions equipped with starshades or coronagraphs aim to block the overwhelming glare of a star so that the dim light of its planets can be seen directly. For the first time, humanity may capture images of pale blue dots orbiting distant stars, not as guesses or shadows, but as worlds revealed in the dark. If those stars turn out to be siblings of the sun, then each discovery will feel like opening an old family album, finding cousins hidden across the galaxy. The scale of this effort is staggering, but so is the potential reward. By mapping the stars with Gaia, by testing their chemistry through spectroscopy, and by peering into their planetary systems with Webb and beyond, astronomers are weaving together a cosmic genealogy. Each new tool sharpens the picture, reducing the chances of mistaking coincidence for kinship, and raising the hope that somewhere out there, around a sibling star, a planet might shine with oceans, clouds, and the possibility of life. The story of this search does not stop at technology alone. Each measurement, each new method, becomes a bridge that carries us further, drawing us closer to the origins of the sun and to the question of whether Earth is truly unique. The search for the sun's missing companion began with unease, with scientists noticing that life's history did not always seem to flow in smooth lines. Extinctions appeared to cluster, like faint echoes of a hidden rhythm. That suspicion gave rise to the idea of Nemesis, the imagined star of death whose slow orbit could scatter comets inward. It was a dramatic hypothesis, and for a time it offered a tidy explanation for why life seemed to suffer great collapses at intervals. Yet, as the data grew, so too did the doubts. Patterns that once seemed clear began to blur. Extinctions were real enough, but their timing proved less precise than the earliest graphs suggested. The beat that looked so steady at first dissolved into irregularity under closer study. Telescopes that scanned the cold outer reaches of the solar system revealed nothing like a hidden star. With every observation, the once feared nemesis faded further into the realm of speculation. The lesson was sharp. Even an idea that captivates the imagination must bend to evidence. The search revealed not only the limits of human pattern seeking, but also the strength of science itself, which grows stronger when it questions its own stories. But the end of Nemesis did not close the door. Instead, it opened another one. If the sun was not accompanied by a deadly twin, what about the other stars it was born with? The search for destruction gave way to a search for family. Astronomers turned their eyes across the galaxy, hunting for the sun's sibling stars that share the same birth cloud, the same inheritance of elements scattered by ancient explosions. Where Nemesis offered fear, siblings offered connection. These two paths, one dark and one bright, together reshaped how Earth is understood. Nemesis taught caution, showing that the fossil record can mislead, that extinction science must be tested and retested, and that the sky holds no simple metronome of doom. The sibling search, by contrast, brought forward a sense of kinship. It revealed that the sun was not a solitary child of the galaxy, but one among many, born in a cluster that dispersed long ago. Tracing those siblings helps explain why Earth carries the chemistry it does, and why it became a place where life could emerge. What emerges from both stories is not a final answer, but a more layered picture. The Earth is not simply a world that survived chance impacts or random accidents. It is part of a chain of cosmic events. Ancient stars exploded, scattering the atoms that built our seas and bodies. The sun formed in a crowded nursery where its siblings shared the same mixture. Time and gravity then scattered that family across the Milky Way. Alongside these truths is the recognition that not every pattern is real, and that imagination must always be checked by the discipline of observation. Each new discovery builds on this foundation. Every sibling star identified adds detail to the sun's early environment, like a page torn from a long-lost diary. Every analysis of extinction patterns sharpens our understanding of how fragile life can be. The disproving of Nemesis is not a dismissal, but part of the process, a necessary clearing of the path so that other, richer stories can emerge. Together, the lessons show that Earth's history cannot be told by a single cause or a single idea. It is a tapestry woven from the interplay of chance, cosmic inheritance, and scientific curiosity. And this tapestry still has threads being pulled. The search for siblings continues, mapping the galaxy with exquisite detail. Extinction research continues, refining the timelines of life's great losses. The interplay between what was imagined and what is real has shaped entire fields of science. The story is not closed, it is unfolding. These lessons, born from Nemesis and from siblings alike, prepare the ground for something larger. They reveal not only facts about Earth's past, but also how science itself moves forward, driven by questions as much as by answers. And it is here that the focus shifts from the discoveries themselves to the impact they left on science and culture, and how the echoes of these searches continue to influence the way humanity looks at the sky. The story of Nemesis did not end when the evidence against it grew strong. Even as the theory was set aside, its influence lingered, shaping how scientists thought about Earth's past and how they prepared to search the skies for hidden threats. Sometimes, even an idea that turns out to be wrong can leave a deep mark, sharpening the questions that are asked and the tools built to answer them. When Nemesis was first proposed in the early 1980s, it offered a bold explanation for the strange suggestion of patterns in the fossil record. If a companion star was tugging at the distant Oort Cloud every 26 million years, it could shower Earth with comets and trigger cycles of extinction. The possibility was haunting, yet it gave researchers a lens through which to re-examine the evidence of life and death written in stone. Suddenly, paleontologists and astronomers were speaking the same language, bridging the worlds of fossils and stars. In the years that followed, scientists pored over extinction data with fresh eyes. They looked more carefully at the timing of events, tested new methods for counting and categorizing ancient species, and refined their timelines with greater precision. Even when the neat cycle unraveled, the work it inspired left behind a stronger foundation. It showed how easy it is to find patterns where none exist, and how important it is to challenge those patterns with data. The Nemesis debate forced paleontology to grow more rigorous, to test its rhythms against better clocks, and in doing so, it deepened our understanding of Earth's fragile history. Astronomy, too, was changed. The search for a dark twin drove the development of surveys designed to uncover faint, hidden objects in the outer solar system. Infrared telescopes scanned the skies, looking for stars too cool to glow in visible light. Space missions like WISE built maps of extraordinary detail, cataloging countless stars, asteroids, and brown dwarfs. Nemesis itself never appeared, but the instruments built to find it revealed an even richer universe, filled with surprises that might otherwise have remained unseen. The very act of searching for something that was not there taught astronomers how to look more deeply, how to rule out possibilities with confidence, and how to prepare for the dangers that truly do exist. Beyond the laboratory and the telescope, Nemesis also shaped the imagination of culture. It appeared in novels, films, and speculative works, embodying the idea that the universe might hold hidden threats, silent forces that could one day erase us. For many, the thought of an unseen twin star stirred a kind of existential unease. It reminded people that Earth's safety has never been guaranteed, that our planet has endured catastrophe before and might again. Even as science ruled Nemesis out, the story left an imprint on the public mind, a symbol of how small and exposed our world can feel against the backdrop of space. There is value in this, too. Fear can drive attention, and attention can drive discovery. Because Nemesis captured both scientific and cultural imagination, it opened doors for conversations about cosmic hazards. It made the public more aware of the possibility of comet impacts, and it made scientists more determined to track near-Earth objects with greater vigilance. It added urgency to the study of asteroid defense, not because a twin star was threatening us, but because the history of impacts written on Earth's surface shows that danger is real. In this way, Nemesis is still affecting Earth, not through the pull of gravity or the fall of comets, but through the legacy of curiosity it left behind. It reshaped paleontology's methods, advanced astronomy's instruments, and planted in the culture a heightened sense of how fragile our place in the cosmos truly is. Though disproven, it remains a reminder that even discarded ideas can shape the path of science, guiding us closer to truths more subtle and more beautiful than we first imagined. And so the story continues, moving from the ghost of Nemesis to the broader family of the sun's siblings, scattered across the galaxy, waiting to reveal more of Earth's origins. When the sun was young, it did not rise alone from the swirling cradle of dust and gas. Around it, dozens, perhaps even hundreds of stars were born, glowing as newborn embers in the same crowded nursery. For a time, they would have shone close together, their light mingling across the same patch of sky. But like all families in the galaxy, they drifted apart, pulled by the restless tides of gravity, until each star wandered into its own solitary path. Today, those siblings are scattered across the Milky Way, separated by distances so vast that they no longer recognize one another. Yet there is a haunting question that lingers. What if the sun had never left them? What if it had remained inside the dense cluster where it was born? To imagine this is to imagine a sky unlike any we know. Instead of a single, steady sun ruling the day and a faint scattering of stars at night, Earth's heavens would have been crowded with blazing companions. Some would have burned with the brilliant blue light of massive stars, others with the steady orange of smaller suns. The night would never have been truly dark. But beauty in the cosmos often comes with danger, and such a neighborhood would have been anything but safe. Massive stars burn fiercely and briefly, and their lives end in violent explosions called supernovae. In a dense cluster, these blasts would have happened close enough to flood young Earth with lethal radiation. Even a single nearby supernova could strip away an atmosphere or sterilize the surface of a planet. In a crowded cluster, there might have been several within a short span of time. It is possible that Earth, if it had even managed to form, would never have been able to hold on to the fragile conditions that make life possible. Then there are the dangers of gravitational encounters. Stars passing near one another tug at the delicate disks of gas and dust that surround them. These disks are the nurseries of planets, but in a crowded environment, their structure can be ripped apart before worlds have a chance to form. Even if Earth had begun to take shape, the close brush of a sibling star could have disturbed its orbit, pulling it closer to the sun to bake dry, or farther away into the icy dark. In such a place, planetary systems are fragile, their harmony easily broken by the passing weight of a neighbor's gravity. Radiation storms would have been another hazard. Massive stars pour out intense streams of charged particles, bathing nearby regions with energy far beyond what Earth receives from our sun today. These storms can strip atmospheres bare, erode oceans, and make the surface of a planet uninhabitable. In a dense cluster, filled with luminous giants, radiation would have been an ever-present threat. It may be, then, that the sun's journey away from its birthplace was the very thing that allowed Earth to survive. By drifting outward, leaving behind the brilliant but dangerous stars of its youth, the sun carried with it the chance for planets to remain stable, for atmospheres to endure, and for life to take root. Distance became protection. Solitude became survival. This irony deepens the story of Earth's origins. The sun's siblings may still exist, shining brightly in distant corners of the galaxy, but their companionship might have been fatal had they remained close. By scattering, the family created space for worlds like ours to grow undisturbed. In this sense, the very loneliness of the sun may be the reason Earth was able to cradle oceans and forests, and eventually the fragile spark of life. And so, the question of what might have been leads naturally to the stories we tell about what is real. While science fiction often imagines skies filled with twin suns and crowded stellar neighborhoods, the truth is that solitude offered the sun a safer path. To understand this contrast more fully, we can turn to the ways culture has embraced the idea of nemesis and solar twins, weaving fiction and speculation into a mirror for our fears and hopes about the universe. The idea of Nemesis, the sun's dark twin, has always carried a kind of haunting power. Even when the science behind it began to crumble, the story lived on, not in data or telescopes, but in imagination. Writers and filmmakers seized upon the thought of a hidden star, circling unseen in the deep, waiting to unleash chaos on Earth. In novels, Nemesis became the perfect villain, a cosmic figure that could explain mass extinctions, sudden disasters, or apocalyptic endings. On the big screen, it sometimes took the form of a second sun rising over a doomed horizon, or a fiery companion dragging comets into a deadly fall. The name itself, borrowed from the goddess of retribution, gave it an air of inevitability, as though destruction were fated to return again and again. Science fiction thrives on possibilities, especially those that blur the line between what might be and what is known. The notion of an unseen twin star was fertile ground because it felt plausible. Most stars really are born in pairs, and comets really do strike Earth, leaving scars that can still be seen on the moon and craters carved into continents. It did not take much for imagination to stretch the science into myth, filling the gaps with dread and drama. For readers and viewers, Nemesis was not just an idea, but a mirror of fear itself, that the universe is vast, uncaring, and full of forces we cannot control. Yet, when the lens shifts from fiction back to reality, the story changes. The truth is quieter, but in many ways more profound. Nemesis as a death-bringing twin was ruled out, yet the sun was not born alone. Its real siblings are scattered through the galaxy, not hiding close by with menace, but drifting far away with memories of a shared beginning. They are not agents of destruction, but keepers of history, carrying the same chemical fingerprints, the same inherited dust of long-dead stars. Instead of a single shadowy companion, the sun's family is vast, spread out like an invisible constellation of kin. This contrast between story and science is striking. Fiction gave Nemesis a personality, a dark presence plotting Earth's downfall. Reality offers something subtler, yet perhaps more moving, a recognition that Earth itself is the product of cosmic family ties. Heavy elements forged in ancient explosions enriched the sun's birth cloud, shaping the chemistry of our oceans and air. Siblings born beside the sun may still shine in distant corners of the Milky Way, and some may host planets of their own. These truths carry their own awe, not through fear of doom, but through the quiet recognition of connection. Science fiction often asks what would happen if catastrophe arrived from the stars. Science reality shows that catastrophe already has in the form of asteroid impacts and mass extinctions, yet it also reveals that survival is possible because of how the sun's path unfolded. Fiction imagines the twin as a looming threat, while science reveals that drifting apart from the family may have been the very reason Earth endured. Both threads, though different, serve a purpose. The fictional nemesis awakens curiosity and fear, sparking stories that reach wide audiences. The real siblings expand our perspective, reminding us that Earth is not isolated, but part of a galactic story millions of years in the making. In this way, imagination and science weave together, one feeding the other. Fiction invites us to ask bold questions, and science steps forward with answers that may be quieter but no less extraordinary. The awe that comes from reality is gentler, yet it lasts longer. Instead of a hidden star of doom, we are left with the vision of a sun once surrounded by family, its siblings now scattered like sparks across the galaxy. Somewhere among them may orbit other worlds, perhaps even ones with oceans and skies of their own. That is not a tale of destruction, but of possibility, and it may be the most inspiring story of all. Science is often imagined as a march towards certainty, a straight line from question to answer. But in truth, it is a living process, filled with detours, revisions, and ideas that blaze brightly for a time before fading away. The story of Nemesis is one of these. It began as a bold hypothesis, captured attention across disciplines, and then slowly unraveled under the weight of new evidence. Yet its fall was not a failure. Instead, it became a reminder of how science grows strongest, not by clinging to ideas, but by letting them go when the facts demand it. When Nemesis was proposed in the early 1980s, it had all the marks of an elegant solution. Fossil records hinted at repeating rhythms of extinction. Comets were known to lurk in the distant Oort Cloud, ready to be nudged inward. A hidden companion star circling the sun could tie these pieces together in one sweeping explanation. The theory spread quickly, bridging paleontology, astronomy, and even popular imagination. It seemed to offer clarity, as though a single unseen actor had been pulling the strings of life and death on Earth for millions of years. But as the years unfolded, careful analysis began to chip away at the foundation. The fossil record, once thought to reveal neat cycles, revealed instead a story more irregular, a history punctuated by catastrophe, but not bound to any cosmic clock. Astronomers turned their instruments outward, searching the sky for the faint glow of a red or brown dwarf star. Infrared telescopes scoured the heavens, and the WISE mission swept across the entire sky in exquisite detail. The silence was unmistakable. No companion star existed where Nemesis should have been. This was the moment when the strength of science revealed itself. Rather than clinging to a theory because it was neat or satisfying, researchers allowed the evidence to lead them. Nemesis was set aside, not out of disdain, but out of respect for truth. And in its absence, astronomy advanced. The very instruments designed to search for Nemesis uncovered countless other treasures. Distant galaxies, faint stars, brown dwarfs drifting quietly in interstellar space. The work sharpened our ability to measure and map the cosmos, skills that now serve in fields far beyond the original hunt. In this way, Nemesis became a cautionary tale. It showed how easy it is for humans to fall in love with patterns, to see cycles where none exist, and to build theories around them, but it also showed how science guards against this temptation. The process of peer review, replication, and independent testing acts like a sieve, letting through only those ideas that endure under pressure. Nemesis could not, but in being tested and found wanting, it strengthened the very system that cast it aside. There is something humbling, even beautiful, about this rhythm. Science does not pretend to be perfect at any one moment. Instead, it thrives on correction, always refining, always willing to admit when an idea no longer holds. In this humility lies its power. Theories are born, tested, stretched, and sometimes broken. What remains is not failure, but a clearer picture of reality. The legacy of Nemesis is proof of this. Though it did not survive as an explanation, it inspired collaborations across fields, drove the creation of better tools, and opened doors to new discoveries. It reminded scientists that the universe does not bend to our desire for neatness, but instead asks us to approach it with patience, rigor, and curiosity. The sun may not have a dark twin, but in searching for one, humanity learned how to listen more carefully to the whispers of the stars. And with that listening came the realization that the sun's true family was not a single shadowy companion, but a scattered clan of siblings spread across the Milky Way. From the end of Nemesis rose the beginning of a new quest, one that continues to shape how we see our place in the galaxy. To piece together the sun's hidden past, scientists now face a task that feels both astronomical and deeply personal: to rebuild its family tree. Unlike the simple branches of a human lineage, this tree stretches across light years and billions of years, with its members scattered like sparks from a fire carried away by the wind. Each sibling star is a fragment of a story that began in a crowded nursery, a cluster of gas and dust that collapsed into light long before Earth ever existed. To trace that family is to uncover the sun's true childhood. The work begins with numbers. Astronomers estimate that the sun was born in a cluster that may have contained dozens, perhaps even hundreds, of stars. They were cradled in the same dense cloud, nourished by the same elements, and set spinning together in the gravity of their shared birthplace. But over time, the cluster dissolved, its stars drawn apart by the tides of the galaxy. What once was a family that shared a single sky is now a diaspora of siblings scattered in every direction. The challenge is to find them, one by one, and to see if they can be woven back into a coherent picture. To do this, astronomers turn to chemistry. Stars carry within them a kind of fingerprint, a pattern in the elements they hold. The proportions of carbon, oxygen, iron, and many trace elements vary from one star-forming cloud to another. But for stars born together, those ratios are nearly identical, like siblings sharing the same DNA. By comparing the spectral lines of thousands of stars, scientists can flag those whose chemical balance matches the sun's. Each discovery adds another possible branch to the tree, yet chemistry is only half of the story. Motion must also be considered, because the stars that once formed a cluster would have moved through the galaxy in similar ways. Over billions of years, gravitational tugs from other stars, from giant molecular clouds, and from the spiral arms of the Milky Way slowly spread them apart. But if astronomers trace their paths backward in time, they can sometimes see those motions converge to a single origin point. The Gaia mission, with its breathtaking catalog of over 1 billion stars, allows scientists to follow these trails with exquisite precision. It is as though the Milky Way itself is being rewound, the stars pulled back into place like beads on invisible threads until their common birthplace appears. This work is painstaking. For every sibling identified, countless other candidates must be examined and set aside. Some stars look similar but are imposters, solar twins that resemble the sun in brightness and color, yet were born far away. Others may be chemically close but follow motions that do not align with the sun's past. To sift through these is to play detective at a cosmic scale, weighing every clue with care. The goal is not only to name siblings, but to reconstruct the full cluster, to understand what the sky looked like on the day the sun ignited. Was the cluster crowded with massive stars, their lives measured in only a few million years before they died as supernovae? Were there smaller, quieter stars, destined to outlive the sun by trillions of years, still glowing faintly long after Earth itself is gone? Each answer sharpens the image of the cradle that made our world possible. Building the solar family tree is more than just a cataloging exercise. It touches on profound questions of connection. To know the sun's siblings is to know the larger network of stars that shared the same cosmic inheritance, the same metals that formed our oceans and bones. It is to see Earth not as an isolated miracle, but as part of a cluster of possibilities scattered across the Milky Way. Somewhere among those siblings, planets may circle quietly, some barren, some stormy, perhaps one or two even carrying their own fragile forms of life. In this way, the family tree is not just a record of the past, it is also a guide to the future, pointing astronomers toward the most promising places to search for worlds like ours. By finding the stars that share our origin, scientists hope to understand not just how Earth was born, but whether it is unique among its kin. The story of the Sun's family is therefore still unfolding, a mystery with roots deep in time, but branches stretching far into the unknown. When astronomers speak of the Sun's siblings, they are not just listing stars on a chart, they are giving humanity a new place in the story of the cosmos. For so long, it was easy to think of the Sun as unique, a solitary lantern set alight to warm Earth alone. Its constancy, its solitary presence in our sky, gave it an air of singularity. Yet the more scientists uncover about its origins, the clearer it becomes that the Sun is not an exception, but part of a greater family. This realization quietly reshapes how we see ourselves. To say the Sun had siblings is to admit that our story is not isolated. It is one chapter among many, written in the same burst of creation. The thought carries a strange comfort. Somewhere in the galaxy, stars that once shared the Sun's nursery now shine in other skies, each with their own surrounding worlds. Some of those worlds may be barren, some may be storm-tossed, and some may hold seas and skies not so unlike our own. To imagine such places is to widen the circle of belonging, to feel Earth connected not just to the Milky Way in a broad sense, but to a specific cluster of stars bound by shared birth. This perspective humbles and enlarges us at the same time. For centuries, humanity placed itself at the center of the universe. Then we learned that Earth revolves around the Sun, and the center shifted. Later, we found the Sun to be only one star among hundreds of billions, and the center vanished altogether. Now, the discovery of solar siblings adds yet another layer. We are part of a family of stars, not solitary, not central, but connected. In that web of kinship, we find meaning in belonging rather than in being singular. There is something profoundly human in this realization. On Earth, we measure our lives through family ties, through bonds of kinship and shared origin. To know that our own star has a family of its own extends that idea outward into the cosmos. It suggests that belonging is not just a human invention, but a universal pattern. Stars themselves form in groups, break apart, scatter, yet remain linked by memory written in their chemistry and their motions. Our Sun's siblings are not near enough to be seen with the naked eye, but they remain a part of us, etched into the very atoms of our world. This sense of connection deepens when we think of what those siblings may carry. Some may cradle planets of their own, with oceans, mountains, and skies lit by familiar golden light. If life could emerge here, then perhaps, under the same chemical inheritance, it might have flickered into being elsewhere. To imagine other worlds circling sibling stars is to glimpse the possibility of cousins far beyond Earth, life that shares with us the same cosmic ancestry. Even if we never meet them, the thought expands our sense of what it means to be alive in a galaxy so vast. For humanity, the search for solar siblings is not only a scientific pursuit, it is also a story about identity. It tells us that we are not the product of a solitary star, but of a network of stars born together in a crowded nursery billions of years ago. It reminds us that the forces shaping Earth did not begin here alone, but were shared across a wider family, This shifts our sense of home from being narrowly defined by one planet to being part of a galactic heritage. And in this shift, there is a quiet beauty. When we look at the night sky, scattered with stars that seem so separate, we now know that among them may be brothers and sisters of the Sunday. Their light is ancient, but it carries a message that even across unimaginable distances, connection endures. To reflect on that is to feel a kinship not only with the stars, but with the universe itself, as though humanity is part of something far greater than its own fragile world. The meaning of solar siblings, then, is not only scientific, it is a reminder of belonging. It is the knowledge that Earth and its people are not an accident adrift in endless space, but part of a family story written in starlight, a story still unfolding across the Milky Way. The discovery of the Sun's lost siblings is not only a story about the past, it continues to shape the way science views Earth and its place in the galaxy today. Each sibling identified and each fragment of chemical evidence uncovered becomes a tool, a clue that sharpens the questions we ask about life and about the fragile conditions that allow it to exist. These insights ripple outward into planetary science, into astrobiology, and even into the way we think about our future as a species. When astronomers trace the chemical fingerprint of a star and realize it was born beside our sun, they are not just cataloging another point of light. They are reconstructing the environment that made Earth possible. The elements in our oceans, in our crust, and in the air we breathe are not random. They are the direct result of what happened in the crowded nursery where the sun was formed. By studying its siblings, scientists can piece together what that nursery looked like and how its conditions gave rise to a world capable of supporting life. This is more than history, it is the foundation of habitability itself. Astrobiology, the field that searches for life beyond Earth, leans heavily on this kind of knowledge. To ask whether life might exist elsewhere in the galaxy is to ask how common Earth-like conditions truly are. If the sun's siblings are scattered across the Milky Way, each shining with nearly the same chemical makeup, then each one may host planets built from the same essential ingredients. Carbon, oxygen, iron, and other elements that made Earth fertile for life would be present there as well. This widens the stage on which the drama of life could play out, raising the possibility that Earth's story is not unique, but one verse in a far larger song. The influence of these discoveries also reaches into planetary science, where researchers study how planets are born, evolve, and sometimes perish. By comparing our solar system with others around sibling stars, scientists can begin to separate what is common from what is rare. Is the presence of liquid water on Earth's surface a fragile accident, or a likely outcome of being formed in a particular type of stellar neighborhood? Did the sun's siblings also inherit the same balance of conditions, or do most of their planets remain lifeless and barren? Each answer refines our understanding of how delicate or robust the conditions for life really are. This line of inquiry has practical consequences. The more we understand about how Earth came to be habitable, the more we can anticipate the factors that might threaten that habitability in the long term. The sun's siblings, scattered across the galaxy, act as silent witnesses to those shared beginnings. By studying them, we gain perspective on the forces that made Earth resilient and the ones that might undo that resilience. This helps guide models of climate, planetary stability, and the likelihood of catastrophic events. In this way, the search for siblings is not only about distant stars, but about protecting the fragile balance of our own world. There is also an emotional resonance to this knowledge. To know that Earth is tied to a wider family of stars makes the planet feel both precious and less alone. It reframes humanity's vulnerability by placing it in context. Our world has always been fragile, but it has also always been part of something larger. That larger story stretches across the Milky Way, binding us to stars we may never see with the naked eye, but which remain connected to us all the same. Even now, missions like Gaia and instruments capable of reading the fine details of stellar chemistry continue to expand this work. Each new discovery is not just another entry in an astronomical catalog, it is another thread in the tapestry of Earth's origin story. As these threads are woven together, they give scientists a clearer picture of where we came from, how life took hold here, and what might await in other corners of the galaxy. Knowledge of the sun's siblings, then, is not an abstract curiosity. It is an active part of how science frames the search for life, the protection of Earth, and the understanding of what it means to belong in a universe filled with stars. From the moment the sun was born, scattered light carried across the galaxy has been reminding us of our origins, and today it still guides the way we look outward, searching for echoes of ourselves among the stars. The search for the sun's lost family is far from over. In truth, it is only just beginning. What we know today is like the first strokes on a canvas, outlines waiting to be filled with color. The next decades promise to bring instruments and missions so powerful that they will reshape our picture of where the sun came from and how its siblings are scattered through the Milky Way. The story of the sun's family tree is not finished. It is unfolding, one observation at a time. One of the most ambitious projects leading this search is Gaia, a spacecraft launched by the European Space Agency. Gaia has been mapping the positions and motions of more than 1 billion stars with a precision never before possible. Each point of light is recorded not as a static image, but as a moving body with its own trajectory through space. By tracing those motions backward in time, astronomers can reconstruct where stars were millions or even billions of years ago. This allows them to identify which ones once clustered near the sun in its nursery. Already, Gaia has given hints of stars that could be true siblings, and as its mission continues, the detail will only sharpen. It is as though Gaia is sketching a family portrait, pixel by pixel, across the entire sky. But Gaia is not working alone. Spectroscopy, the study of how stars absorb and emit light, continues to act as the cosmic fingerprinting tool. Each sibling of the sun carries in its light a unique blend of elements, the same recipe of carbon, oxygen, iron, and other building blocks forged in the environment where the sun was born. Future telescopes, equipped with more sensitive spectrographs, will allow scientists to compare these chemical fingerprints with exquisite accuracy. With them, the process of identifying siblings will become more like reading DNA, confirming family ties across vast stretches of the galaxy. The James Webb Space Telescope, though famous for peering into the earliest galaxies, is also part of this search. With its infrared vision, Webb can study faint and distant stars with a clarity impossible from Earth's surface. It can look through the dust that often hides stellar nurseries, giving us a view of young clusters that mirror the one our sun once called home. In the years ahead, Webb and its successors will not only trace siblings, but also examine their planets, asking whether worlds like ours orbit under skies once linked to our own. Beyond Webb, future observatories are already being planned. Telescopes like the extremely large telescope in Chile and the 30-meter telescope in Hawaii will peer deeper and sharper into the cosmos than anything built before. They will gather light with mirrors so wide they could hold a city street within their span. With this light, they will dissect starlight in greater detail than ever, revealing sibling stars with unmatched certainty. Each discovery will be another piece of the sun's long-lost family returned to view. The next generation will also expand the search beyond stars to their planetary systems. Space missions like Plato, designed to hunt for exoplanets around sun like stars, may find Earth sized worlds orbiting our siblings. Imagine discovering a planet with oceans and continents under the glow of a star that once shared the same cloud of birth as our own Sunday. Such a discovery would change not only how we view Earth's place in the galaxy, but how we understand the possibilities for life itself. These coming decades hold the promise of revelations that may feel both familiar and alien. Perhaps dozens of siblings will be identified, scattered like distant cousins across the spiral arms of the Milky Way. Perhaps some of them will be found with planets rich in water, or even conditions suitable for life. Each of these discoveries would not only expand our understanding of the sun's story, but would also deepen the story of Earth, reminding us that we are part of a much larger family of worlds and stars. The search ahead is a patient one, unfolding slowly as technology grows more powerful and observations accumulate. Yet with each new advance, the fog clears a little more. The sun's childhood, once hidden by billions of years of time and distance, is beginning to reveal itself. And in that revelation lies the possibility of finding not just stars that resemble the sun, but true siblings that once burned beside it, whispering secrets of our own beginnings. Even though Nemesis was never found, and most scientists now agree it almost certainly does not exist, the idea left a deep mark on science. Sometimes, even a wrong path leaves behind important lessons, shaping the way we see the universe and ourselves. Nemesis was not just a star imagined in the darkness, it was a story, one that captured the minds of scientists and the public alike for decades. The name itself carried weight. Nemesis, in ancient Greek mythology, was the goddess of retribution, punishing those who grew too proud. To give a star this name was to suggest that the cosmos itself might deliver punishment from the sky. For many people, the thought that a hidden twin of the sun could silently govern cycles of destruction on Earth was terrifying, but it was also fascinating. It made the sky above feel alive with secret intent, as if it held a power beyond our control or even our understanding. When the hypothesis first appeared in the 1980s, it spread quickly beyond the walls of universities and research centers. Newspapers carried headlines about the Death Star lurking in the solar system. Popular magazines speculated about when the next wave of comets might be unleashed. Novelists and filmmakers wove the idea into their stories, building worlds where Nemesis returned to rain catastrophe upon Earth. For a time, Nemesis was more than a hypothesis. It was a cultural figure, haunting both scientific journals and works of fiction. The power of this story did not come only from fear. It also came from the way it highlighted how fragile Earth truly is. If comets could be sent our way by the motion of a distant star, then our planet was not as safe as it seemed. Life on Earth, which feels so solid and permanent, could be overturned by forces that operate far beyond our skies. Nemesis forced people to think of extinction not just as an event in the deep past, but as a process that could be written into the very rhythms of the cosmos. In laboratories and observatories, Nemesis also left its imprint. Scientists designed surveys, built instruments, and combed through data partly to prove or disprove its existence. Whole teams devoted years of work to scanning the heavens for faint red dwarfs or brown dwarfs that might fit Nemesis's description. Even though they found nothing, the act of looking expanded our knowledge. It taught astronomers how to map the sky with greater care, how to refine models of stellar orbits, and how to measure the subtle signatures of distant objects. In this way, Nemesis acted almost like a teacher, pushing science forward by the very effort of being tested. The fossil record, too, was seen with new eyes. Patterns that seemed like cycles of destruction were re examined again and again as researchers debated whether life on Earth really followed a cosmic clock. That debate sharpened the tools of paleontology and statistics. It forced scientists to ask harder questions, to check and recheck their methods, and to accept that nature does not always fit neatly into patterns. Nemesis may have been a mirage, but in chasing it, science became stronger. Even today, when Nemesis has largely been set aside, its shadow lingers. People still imagine what it would mean if such a star did exist, if somewhere in the vast ocean of space the sun's twin still drifted unseen. The idea continues to appear in books, in television, and in films. It continues to whisper through the culture as a reminder that the universe holds mysteries beyond our reach, and that our place within it is not guaranteed. In a quieter way, Nemesis remains a symbol. It stands for the human urge to connect what happens on Earth with the wider motions of the cosmos. It reflects our fear that disasters may not be random, but written into the fabric of space itself. And it reminds us of humility, that even the most elegant idea must stand against evidence, and sometimes fall away. What endures is not Nemesis itself, but the lesson it carried. Earth is fragile, life is vulnerable, and the universe is vast, full of forces we are only beginning to understand. The search for Nemesis, even in failure, deepened our sense of how thin the boundary is between stability and chaos. It taught us that the story of Earth is shaped not only by what lies beneath our feet, but by what moves silently in the stars above. The story began with a haunting question. Was the sun ever meant to be alone? For billions of years, it has shone steadily, carrying the rhythm of life on Earth, rising and falling with a faithfulness that shaped our days and our dreams. Yet hidden in its past was the suggestion of another, a twin that might have shared its birth, a shadowy partner that some once thought could bring waves of destruction across the ages. That twin, Nemesis, was never found. The Death Star that newspapers once warned of did not appear in the sky, and the search for it revealed no lurking companion steering comets toward our fragile world. Yet, the idea left its mark, for in reaching to disprove it, science uncovered something even richer. The sun did not rise alone from its birth cloud. It had siblings, perhaps dozens or hundreds of them, scattered now across the galaxy like sparks from the same ancient flame. Every atom of Earth, every drop of ocean, every breath of air carries that shared heritage. Long ago, in the fire of a nearby supernova, carbon, oxygen, and iron were forged and mixed into the nursery where the sun and its family began. Without that cosmic inheritance, there would be no seas, no mountains, no forests, no fragile strands of DNA. The Earth itself is a child of those forgotten stellar kin. The sun's lost twin may not haunt our sky, but in a deeper way, it still touches us. It lingers in the questions we ask, in the science we build, and in the imagination that leads us to wonder whether life might exist under the glow of a sibling star. Even when disproven, Nemesis reshaped astronomy. It sharpened the tools of extinction science, pushed technology to search for hidden companions, and forced us to look again at the delicate balance that keeps life on Earth secure. This is the quiet power of science. It thrives not only on answers, but on the questions that lead us astray, on the mysteries that open new doors even when the old ones close. The search for Nemesis taught us humility, but it also deepened our connection to the wider universe. It showed that Earth is not an isolated accident, but part of a much larger story, a family story written in starlight. So when we gaze at the night sky, we might remember that the sun's lost twin is not above us tonight, yet its story lives on in every atom that makes us who we are. The echo of that forgotten star runs through the oceans, the soil, and the fragile spark of life itself. The true legacy of Nemesis is not destruction, but the reminder that we are bound to the cosmos in ways far greater than we can see. Before we drift to a close, I would love to know where in the world you are listening from and what time it is for you. It always amazes me to imagine this story being shared across so many skies at once, with one small flame of curiosity connecting dreamers all over the earth. If this journey has brought you calm or wonder, it would mean a great deal if you gave this video a gentle like and perhaps subscribed for more sleepy science stories to come. So now, take a slow breath. Let the questions linger. Let the stars above carry you deeper into rest. And together, let us carry forward the story of the sun's forgotten other half, still shaping us, still reminding us that in every heartbeat and in every atom of Earth, we are part of a much greater universe.